Alright, I'm back playing with my system here. I know you guys asked a question yesterday about the comp block, and I actually don't know enough about my comp block to explain it all to you, so I've been playing with it this morning. I gotta get going here, but I wanted to try a few things. And I added fixed losses. That seems to be important too, so I might have to work on a fixed loss. I know Rockwell had fixed losses. I didn't know if I needed them or not, so I think I do. Anyway, that's another story. They just have a lookup table based on motor RPM. It's pretty easy. So what I got is I put in an on-off bit for the comps, so the torque set point goes from zeroed, and then if it's turned on, I put in my math, and then I've got a small filter because the way I'm doing it now, it just sends all this torque to the drive immediately, so I need a little bit of a ramp to get it so it doesn't trip. But I got my trend, which isn't running. All right. So we'll do a run command. And now we have no comps. So what you see, and it's not very exaggerated without load on the motor, but there's a little bit of a delay. And that's the speed regulator integrating, and then it quickly catches and starts working. So it looks good. It looks good on the bench, actually. It's not horrible. And so the math is still on the screen. It's not contributing anything. And it rounds in at full speed, no problem. And then we go back and we turn it off. Okay. And it works fine without comps. Oh, and the other thing is I have super low gains. I have a 1 per unit, a proportional, and only 100 milliseconds of integral, which in the real world, those would probably be more like 5 maybe on proportional, 2500 on integral, somewhere in that range. So, but using slow regulator gains allows the drive to not bang couplings and work. You want the regulator to be slow because of the mechanical side of the machine, the gearbox slash and all that junk. That's another thing I can't simulate is the gearbox slash. So now we'll start it with the comps on. Comps are on, yep, okay. Give it a run command. And of course it's an unloaded motor, so it's kind of hard to see it, but notice how speed and reference are kind of on top of each other. That's that initial hitting it of that compensation. Might have to work on a ramp or something for that. But we got this little bit of a delay, and that's the speed regulator integrating up to produce torque. But if you calculate the torque, you don't have that delay, so you're right on the reference, which I know it seems kind of minor here, but man, if this doesn't work on a paper machine, it's a bummer. So that's what I've been working on. I don't have much more to show. I did go into the compensations here, and these KFF is the axle in seconds, essentially, for the math. So KFF is inertia seconds. That's the total amount of seconds at 100% torque to get to full speed. And this is an unloaded motor, so a tenth of a second at 100% current. I mean, this motor spins up so quick. I actually don't even disbelieve it. But on the bigger machine, I expect it'll be more like 5 seconds, 10 seconds. We'll see. I might try some of this, run it, because I can run this code without actually sending current commands. So that's what I'm thinking I might do. If I got time. My life is pretty hectic when I get to the mill for some dang reason. So again, I got really low speed regulator values, 1 in 100, which nobody would run pretty much, but that exacerbates the speed regulator integration time. And if we had way higher loads where the drives have to hit 60, 70, 80% just to start, that's where this really plays a key role. And then the fixed comps are at 20, so notice the top one is speed reg out, 7%, and the bottom one is the fixed compensation. It takes about 27% obviously to run the motor here on my 9/10 of an amp motor. So I think fixed comps are an important piece too. Anywho, that's what I got. I'll send this file. It's on an unloaded motor. And I think I'll call it good, because I'm going on vacation. Talk to you later.